Hi, this is Somaiah working as assistant professor in the Department of Mechanical Engineering, the Institute of Aeronautical Engineering, Dundigal. Today, I'm going to discuss about fluid kinematics and fluid dynamics. So, in this module, in the beginning, we'll go through fluid kinematics and various types of flows. Its descriptions, examples of types of flows, and methods of flow descriptions. So, these various components we will discuss in this class. So the science which deals with the geometry of motion of fluids without reference to the forces causing the motion is known as hydrokinematics or simply kinematics. So the basically the fluid the motion can be divided into different groups, so like fluid statics, fluid kinematics, fluid dynamics, etc. So, but in fluid statics, what can be studied is that if the fluid is placed at rest, so under that static conditions, we are going to evaluate different properties of a fluid. Then that comes under a fluid statics. So, but if the fluid is caused to move with some forces, some external forces, due to some force, if the fluid is moving, if you study the behavior of a fluid particle or fluid particles in that motion, then you get this comes under a fluid kinematics and fluid dynamics. But if you consider the fluid motion along with the forces causing its motion, then that is known as a fluid dynamics. If the fluid particles or fluid is studied under the motion without causing, without considering the forces causing its motion, that is known as fluid kinematics or hydrokinematics. So here we will discuss the fluid kinematics. So that means the fluid flow will be taking place, but we don't regard the forces, various forces causing its motion, like pressure forces, viscous forces, gravitational forces, inertia forces, etc. We don't regard all these forces which are causing the motion of a fluid, but we will study the characteristics of a fluid. Such type of study is known as fluid kinematics. Thus, kinematics involves merely the description of the motion of fluids in terms of space-time relationship. So, on the other hand, the science which deals with the action of the forces in producing or changing the motion of fluids is known as hydrokinetics or simply kinetics. So the hydrokinetics means it considers the forces, the action of forces which are causing the motion of a fluid. So that is kinetics. Obviously, the study of fluids in motion involves the consideration of both the kinematics and the kinetics. A fluid, unlike a solid, is composed of different particles which move at different velocities and may be subject to different accelerations. Moreover, the velocity and acceleration of a fluid particle may change both with respect to time and space. So, we have to consider space, the particular fluid particle or mass of fluid in a space, and we have to study with respect to the time. So what are the characteristics are going to change, etc. We'll study. So, but in case of a solid, as a whole, the velocity of a solid is going to be calculated or to be evaluated. So, but in a fluid particles, individual particles will be studied. Therefore, in the study of the fluid flow, it is necessary to observe the motion of fluid particles at various points in space and at successive instants of time. So, there are two classes of flow descriptions. The first one is Lagrangian method. Another one is the Eulerian method. So, in Lagrangian method, the individual fluid particles will be selected, and they will be traced over a period of time. So there, it's a study with respect to the space, with respect to the time, whether they are going to change, in what way their behavior is going to be changed, is to be analyzed. That is the that is a Lagrangian method. But whereas Eulerian method, particular fluid mass will be selected, and over a period of time, so these fluid particles at successive positions can be evaluated, but not individual fluid particle, but fluid mass can be selected. So according to this fluid Eulerian method, the particular fluid mass, its characteristics togetherly will be evaluated. So these two are the different methods of a flow description. So, but in general, the Lagrangian method can be adapted. So now we will discuss about the velocity of fluid particles, and afterwards types of fluid flows. So before going to discuss the fluid flows, we should know the velocity of a fluid particle, how to select a fluid particle, and the how do you derive the velocity, how do you measure the velocity of a fluid particle, that we will discuss, and then I will look into the classification of fluid flows. So the motion of a fluid, like that of solid, is described quantitatively in terms of the characteristic known as velocity. So, however, in case of solids, it is generally sufficient to measure the velocity of body as a whole. But in the case of fluids, the motion of fluid may be quite different at different positions of observation. So, in solid as a whole, we have to measure the velocity. But in case of fluid, individual fluid particle velocities, we have to measure. We have to calculate. If you consider about the coordinates x, y, and z in a space, there are three mutually perpendicular axes. So about which the small x, small y, and small z. So these are the coordinates about the principal axis. So about this, at a particular distance of a small x, small y, and small z, the particle is located in this space. So where the coordinate of the particle is x, y, z, small x, y, z. That is the coordinates of that particle location. So then, if you consider the particle is moving from this point to another point, so while it is moving, a fluid particle is moving like this. If it is taking this path, if you have to trace out this fluid particle, and if you need to analyze the characteristics of a fluid particle about this path, about this particular fluid particle, we have to locate it in a space coordinates, and then locate any 2 points as it is moving from point 1 to point 2. There will be two different times, and there will be a displacement as it is moving from one position to another position. There is a displacement, change in position is a displacement, and if you draw a horizontal line, that gives dx a component about x, and dy is a vertical, and the change in position is nothing but ds. So these parameters, these are the displacements about different axes, dx, dy, dz, ds. These are the displacements about different coordinate axes. And small u, small v, small w are the velocity components about three different axes. So for this, we will find out the velocity. How do we calculate the instantaneous velocity? Also, the average velocity. So therefore, the velocity v at any point of a fluid mass is expressed as a ratio between the displacement of a fluid element along its path and the corresponding increment of time as the latter approaches zero. A particular point in the space occupied by a fluid in motion is selected, which may be denoted by coordinates x, y, z, as we have seen in the previous diagram. Since this point is fixed in space, the coordinates x, y, z, and t are independent variables. So the velocity can be expressed for a fluid particle. The velocity can be expressed in the form of a limit of ds over dt as elapsed time approaches zero. The elapsed time approaches zero. Dt is approaching zero. So limit of ds over dt is nothing but the velocity, instantaneous velocity of a fluid particle, where ds is the distance traveled, otherwise a displacement. And similarly, is the velocity where dt is the time traveled from one point to another point. So dt, then we can express v equals to limit of ds over dt as dt is nothing but elapsed time as approaching 0. So that average velocity, or this can be expressed, it can be obtained by using this equation. So the velocity is nothing but change in displacement over change in time. So therefore the position at T2 and minus the position of a fluid particle at T1 time by T2 minus T1. So if the T1 is, we can take the time is T. For T2, the time becomes T plus delta T. So therefore, if you substitute, then we will get a limit as delta T approaching 0. If you substitute T1 and T2 values, we will get a limit of derivative of x with respect to t as a delta t or dt approaching a 0. The velocity is a vector quantity and hence it has magnitude as well as direction. Therefore, the velocity v at any point in the fluid can be resolved into three components. So the capital V can be resolved into three components about three mutually perpendicular directions, x, y, z, and the velocity components are u, v, w respectively. Each of these components can also be expressed by the limiting rate of displacement in the corresponding direction. So thus dx, dy, dz are the components of displacements. Displacement ds in x, y, z direction. So the equations can be expressed about three mutual perpendicular directions. About x, the velocity u, component u, can be expressed as a limit of dx over dt as dt approaching 0, or elapsed time, dt is elapsed time as approaching 0. Similarly, v is nothing but in the direction of y. This is in the direction of x, this is in the direction of y, and similarly in the direction of z. So limit of dy over dt as dt approaching 0. Similarly, w is a velocity component in z direction, limit of dz by dt as dt approaching 0. Now, we will discuss the types of fluid flow, or classification of fluid flows, how many types of fluid flow. While flow is taking place, how can you recognize whether this which type of flow it is? In order to understand, otherwise, in order to identify types of flows, so we have to go through its classifications, so that we can identify based on the type of flow as we see in the real world. Its classification is steady flow and unsteady flow, uniform flow and non-uniform flow, one-dimensional, two-dimensional, and three-dimensional flows, and rotational, irrotational flow, laminar and turbulent flows, compressible, incompressible flows. So still multi number of classifications are there, but as our subject point of view, we are going to discuss these types of flows. So further, still many types of flows are there. So in steady flow, so the steady flow, the particular flow is said to be steady if the fluid characteristics such as velocity, pressure, density, temperature remains constant with respect to time over a period of time. Then we can call it as steady flow. So these will not change with respect to the time in a space. So that is nothing but a steady flow, where velocity of from point to point, if you consider a fluid flow from this point to another point, where velocity, pressure, density, and temperature will not, it should not vary. If the diameter is constant, if the flow is uniform, if the velocity remains constant over a period of time with respect to time. So that's why the steady flow means its velocity, pressure, external pressure, and density, etc. The remaining parameters will not vary about time. So this can be expressed in terms of dou u by dou t is equals to 0. So with respect to time, velocity should not vary. So dou v by dou t, dou w by dou t is also equals to about three mutual perpendicular directions. Pressure is dou p by dou t. The pressure should not vary with respect to time. Similarly, density dou rho by dou t is nothing but density of a liquid. It should not vary. So over a period of time, such type of flows are known as steady flows of fluid. Then the example by this example we can remember the steady flow, a flow of liquid metals. So the liquid molten metals while it is flowing, so whose velocity and other parameters like density will not vary, like salt water, etc., and flow through constant dia of pipe at a constant rate. If the diameter of pipe is constant and we are allowing the constant rate of liquid to flow through that pipe, then the remaining parameters will not vary by neglecting the frictional losses. And the unsteady flow this is just opposite to the steady flow, where velocity, pressure, density, temperature, and other fluid characteristics are varying with respect to the time. If it doesn't vary, then we can call it as steady flow. If they are varying, if they are not equals to 0, every time they will vary at successive instant of times. The velocity, pressure, density, etc., will vary from point to point. So such type of flows we can say unsteady. So because the velocity and other parameters will not remain as same at different timings. Its example is a large flood or failure of a dam. So where in failure of a dam or sudden opening of a tap, then causes unsteady. So yeah, everything its velocity, pressure, it will be disturbed one. So a flow through non-uniform dia. So therefore, continuously, if it is non-uniform means continuously the velocity will vary. So therefore, this comes under unsteady flow. Opening of a valve, flow through orifice meter, where orifice meter is sudden contraction will be there. So throughout pipe diameter, so fluid will flow till that time. So at the orifice, suddenly it has to reduce its area of cross section of a fluid, so it becomes the abrupt flow will be taking place at orifice meter. So therefore, that is also unsteady. So now your uniform flow. The uniform flow means where velocity remains the same throughout its flow. So such type of flow is said to be with respect to time in a space. The velocity remains constant. That is nothing but dou v by dou s equals to 0. There is nothing but a uniform flow. The uniform a flow is said to be uniform if the velocity doesn't vary with respect to time in a space. The uniform flow will constant where dou v by dou s constant and represents any direction of displacement of the fluid element. States that there is no change in the velocity vector in any direction throughout the flowing fluid at any instant of time. So example is flow of liquids under pressure through long pipelines of constant diameter is uniform flow. So long pipeline and at a constant constant rate. So that means it maintains the constant velocity. So therefore, dou v by dou s is equals to 0. This is nothing but a uniform flow. The non-uniform flow means where velocity with respect to the space at any instant of time will vary. So that is represented by dou v by dou s not equals to 0. and its example is flow of liquids under pressure through long pipelines of varying diameters. So is non-uniform. Varying diameter is nothing but velocity will not be same. V1 will vary. Is not equals to V2 is not equal etc. So V is not equals to 0. Therefore, we can call it as if you take a long pipeline of non-uniform diameter, then it causes non-uniform flow. And yeah, as we have gone through steady, unsteady, uniform, non-uniform, and some type of flows will be existing by with the combination of these two types of flows, steady, unsteady, and uniform, non-uniform. Then we will be getting another four types of flows. And this can be added to the earlier divided the flows. So the steady uniform means where velocity, pressure, density, etc. will be remains. The fluid characteristics will remain same. That is steady. But where uniform flow is nothing but in a space with respect to the time, the velocity remains constant. So if you combine these two types of flows, then that gives a steady uniform flow. Similarly, steady non-uniform flow. Steady non-uniform flow means where the velocity, pressure, density, remaining fluid characteristics will remain same, but where it's with respect to the velocity, with respect to the space, the velocity will not remain same. With respect to the space, the some other fluid characteristics will not remain same. Some of the fluid characteristics may same with respect to the time. So unsteady uniform flow. Uniform means where velocity remains constant with respect to, but unsteady means remaining all fluid characteristics will be disturbed. So that is the case of unsteady. Similarly, unsteady non-uniform means with respect to the space, the velocity and the remaining fluid characteristics also every characteristic will vary with respect to the time at any instant of time in a space. So examples, by the examples, we can remember these four classifications: steady uniform, steady non-uniform, and unsteady uniform, unsteady non-uniform. So these four classifications can be remembered by these examples. The flow of liquid through a long pipe of constant diameter at a constant rate. The diameter is constant, and the discharge which is flowing through that particular pipe is also constant. Then that comes under steady uniform. So here a long pipeline of constant diameter remained constant, but whereas the pipe is the through the pipe the flow rate is increasing or decreasing. So therefore, it becomes a non-uniform. The velocity becomes disturbed. Even though diameter is the same, a diameter is constant means we'll get unsteady. Sorry, this is increasing or decreasing means non-uniform. And even though it is a constant diameter, so due to rate of flow variation, Q is not equal to 0. So in that cases, it becomes unsteady and uniform. The uniform means where the diameter of the pipe is constant, then we can call it as a uniform. So as the pipe is constant uniform, but rate of flow is varying, therefore fluid particles are varying, therefore it becomes unsteady. Unsteady due to increasing or decreasing of rate of flow, and uniform because of constant diameter of pipe. A flow of liquid through a tapering pipe at a constant rate. So tapering pipe at every cross section the diameter will be goes on decreasing or increasing, but the constant rate is there. Constant rate of fluid is allowed. So therefore this comes under steady non-uniform. So flow through the tapering of pipe at either increasing or decreasing rate. So both is a tapering pipe, but rate of flow is also increasing, decreasing. So both are unsteady, non-uniform. So unsteady due to the variation in flow rate, it becomes unsteady, and non-uniform due to tapering of a pipe. So with this, we can remember these four classes of flows. Now, three-dimensional flow. Three-dimensional flow in which about three directions, the fluid particles will not vary. The fluid characteristics will not vary with respect to the time. About three mutually perpendicular directions, the flow characteristics such as velocity, pressure, density, temperature, etc. So, in a space, with respect to time, they will not vary. So, such type of flow is known as three-dimensional steady flow. In three-dimensional unsteady flow, these characteristics, fluid characteristics will vary. That is comes under three-dimensional unsteady flow. So if remains same, three-dimensional steady flow. So example is flow through a nozzle. So here, in mathematical form, we can say observe the unsteady three-dimensional flow. So the about x, about y, about z. So these fluid characteristics, fluid particles characteristics will vary with respect to the time. So therefore, it becomes an unsteady three-dimensional flow. In case of steady three-dimensional flow, with respect to time, it becomes a constant. Therefore, it becomes uh, u is f1 of x, y, z. We should not add t because it's a steady three-dimensional. So, with respect to the time, the fluid characteristics will remain same about three directions in a space. So, similarly, two-dimensional flow means we'll consider in this case only two dimensions by omitting z direction. The z direction velocity component becomes zero. So, in unsteady, the fluid characteristics will vary with respect to the time. Then it becomes a two-dimensional unsteady as we are considering x and y directions alone. So then steady two-dimensional means with respect to the time fluid characteristics will not vary. Therefore, it comes under two-dimensional steady flow. Similarly, one-dimensional study also. So, where fluid characteristics will vary with respect to the time about only one direction in a space. Similarly, here we can express the x only in x direction. We can express this. Yeah, and y z becomes zero for unsteady. It will be varying with respect to the time, but in study with respect to the time, the fluid particles remaining constant with respect to that particular direction. Next, rotational flow. In a rotational flow, while fluid particles are moving, they will rotate about their own mass centers. As a flow is taking place, they will move about their own mass centers and they will move along the flow. So, such type of flow is known as rotational flow. The example is varying speed of a rotation of the flywheel of a sewing machine, where if you consider individual particles, then they will rotate about their own mass centers and they will move in a flow also. In case of irrotational flow, the fluid particles, the particles will not rotate about their mass centers. They will be moving over a path or a particular path they will be following, but they will not rotate about their own mass centers. The example is carriages of Ferris wheel. Next, laminar flow. There are three different types of flows as per the renal number: laminar flow, transition flow, and turbulent flow. So, in laminar flow, where the fluid particles will be moving with uh, in a predefined paths without disturbing the other fluid particles paths. So this type of fluid flow nature will be observing in a high viscous fluid movement in fluid moving. So if the high viscous fluids are moving or molten metals are moving, salt water is moving, then we can see at low speed. So each fluid particle will move in its path without coming into the path of other fluid particle and disturbing. So the such type of flow is a laminar flow. In turbulent flow, the fluid particles will move in a random manner, zigzag. In zigzag manner, they will be moving. Therefore, while the fluid particles, while the fluid is moving through a pipe in a zigzag manner, in a turbulent flow, then what happens? There will be a formation of eddies. So the formation of eddies means that leads to a energy loss. Therefore, in the turbulent flow, the fluid particles, they won't have particular path or definite a path. They won't have. They will be randomly moving and causing the energy loss. So such type of flows are turbulent flows. The occurrence of a turbulent flow is more frequent than that of laminar flow. The example is a flow in natural streams, artificial channels, water supply pipes, sewers, etc. are a few examples. Based on Reynolds number, the fluid flows can be classified as per the number. So, as we have discussed previously, the laminar flow, turbulent flow, transition flow. So, as per the Reynolds number, the laminar flow will be existing up to 2000 only. So, up to 2000, the Reynolds number is expressed by rho Vd by mu. The density of a particular fluid, velocity of the fluid, and the diameter of the pipe through which it is moving, and the viscosity. Then, if you substitute these values in Reynolds expression, so then you will get a number. So, if the number is less than 2000, then you can call it as a laminar flow. And if the number is in between 2000 to 4000, then it is comes under transition flow. So if the Reynolds number is exceeding greater than 4000, then this is known as turbulent flow. So where the fluid particles will be moving in a random zigzagged indefinite paths, and therefore, so its Reynolds number is greater than to 4000. So based on the Reynolds number also we can classify the flows, and we can remember the flows. These are the references. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.